Welcome all to SPT online classes. Today we are going to study a topic called interference. Now, in interference, what all things we need to learn? We need to learn about how an interference pattern is obtained, and we also need to know about the conditions of obtaining the bright band and dark band. So that's what we are going to focus in today's session. So here, in order to understand the concept of interference, we need to know about the superposition concept. That means how waves superimpose each other, how they merge each other, and then it gives you a bright band or dark band. So let's try drawing the first wave. So here, as you can see, this is my first wave. Okay, now it needs to superimpose with yet another wave. So let me draw the second wave in such a way that it starts from the same point. Starting from the same point, we say that the phase difference between these two waves is 0, or path difference is equal to 0. So if the phase difference and path difference is equal to 0, then what you can see is that the crests of two waves merge each other, overlap each other, and what you get is a wave with amplitude which is equal to sum of the amplitudes of both the waves. Understood? So the resultant wave will be having an amplitude which is equal to sum of the amplitudes of both the waves. So that means you are getting a bright band. That means you are seeing a phenomenon called as constructive interference. So when crest meets crest, you get constructive interference. As simple as that. Now, when will you obtain yet another constructive interference if the second wave can't start from the same phase? So let's try drawing another case, another diagram. So as you can see here, this is my first wave, but unfortunately, say the second wave cannot start from the same position. Instead, we need to figure out a position from where the second wave can start so that it can still merge with the first wave to get a bright band. So from where can you draw, which point will it be? That point will be after a wavelength lambda. That is the concept. So here you can see, if the second wave starts after a path difference of lambda, then what's happening is that once again the crest meets the crest and you get a bright band. You get a bright band. Understood? So from that we can understand that, okay, the second wave started after a wavelength lambda, it gives a bright band. So again, the second wave, if instead of starting from lambda, if it starts from say 2 lambda, once again you are going to get a bright band, because again you can see the crest meets the crest, and once again you are going to get a bright band. That means the condition for constructive interference or obtaining a bright band is that the second wave should start with a path difference of lambda or 2 lambda, even at 0. So we can say from 0, lambda, 2 lambda, and so on. Thus we can generalize the condition as path difference delta equal to integer multiple of the wavelength where n equal to 0, 1, 2, 3, etc. That's the condition for obtaining a bright band. Understood? That's how you get a constructive interference pattern. Now, what if the wave, instead of starting from the same phase, it started from 180-degree phase? So let me draw that. So here, this is the first wave. Okay, instead of starting from the same phase, the second wave is going to start from the 180-degree phase shift. 180-degree phase shift means basically it's starting from a lambda by 2 path difference. That means it's basically starting from the mid of the first wave. So what will happen? You can see the trough of the first wave meets the crest of the second wave, and thus you get a dark band. A destructive interference pattern is obtained. Understood? So when will this happen again if it can't start from that same point? Say, let's name that point as A. If it can't start from A, from which point, if it should start again to get a destructive interference. That we can figure out how. So let's draw the first wave. Let's continue drawing the first wave for 2 or 3 cycles, and let's draw the second wave. Now this time it should start from a point B, so that now the total path difference will be equal to lambda by 2 plus lambda, which is equal to 3 lambda by 2. That means this time it should start from a path difference of 3 lambda by 2, which is an odd multiple of lambda by 2. So once again you get the trough of the first wave meeting the crest of the second wave, superimposing, getting a dark band or a destructive interference pattern is obtained. Thus again, if you need to get yet another dark band, let me draw that the next time the second wave should start with a path difference of 5 lambda by 2. 5 lambda by 2. That means you are getting a dark band at every odd multiple of wavelength. So you can generalize it now by writing path difference equal to either 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2. Now if I always suggest to pick the first one just because of one single reason, because if you pick the first one, then n where n equal to it starts from 1 2 3 etc. And if you are picking the second one, the problem is that you can choose that, but the problem is it starts from 0. Since we don't have a zeroth dark band in interference pattern, the minimas will be always starting from n equal to 1 onwards, so better prefer the first one. Understood? So that's the condition for obtaining the dark band, that path difference should be equal to odd multiple of the wavelength. Now that's in terms of path difference. What will be in terms of phase difference? It's very easy, because we know that phase difference is after all equal to odd multiple of, phase difference is equal to 2 pi by lambda times the path difference, isn't it? So for bright band we can write the phase difference condition as 2 pi by lambda times n lambda. So what will happen? Lambda gets cancelled and you get 2n pi, isn't it? So either you can say path difference as integer multiple of wavelength, or phase difference as 2n pi. On the other side, for dark band, what will be the phase difference? What should be the phase difference? Phase difference, once again, it should be equal to 2 pi by lambda times 2n minus 1 times lambda by 2, and lambda gets cancelled, this 2 gets cancelled, and you will be left with 2n minus 1 times pi. 2n minus 1 times pi. That means the phase difference should be equal to 2n minus 1 times pi. So let's quickly summarize what we learned today. So we learned about constructive and destructive interference. I haven't mentioned anything about Young's double slit experiment or its interference pattern or its its angular position or bandwidth, that we all can cover in another video. But today's session we basically discussed about the superposition of two waves and getting a resultant wave of amplitude, which is basically the sum of the amplitudes of the individual waves. And here you can see that the crest meeting the crest resulting into a large wave, or we can call it as a bright band or constructive interference, that happens for the integer multiple of wavelength, or in terms of phase difference it is equal to 2n pi. To obtain the destructive interference, the crest should meet the trough, and here you can see at a path difference of lambda by 2 or 3 lambda by 2 or 5 lambda by 2, this keeps happening. So you can generalize it by saying the path difference equal to odd multiple of the wavelength, that you can write in 2n minus 1 times lambda by 2 or 2n plus 1 lambda by 2, but we prefer the first one just because it starts from n equal to 1 and there is no zeroth dark band. That's why we prefer the first one. And finally you get the phase difference phi, which is equal to 2n minus 1 times pi. I hope this topic is clear, constructive and destructive interference. We'll see you in the next video. Thank you.